So, good afternoon, all. My name's Tabitha Binding, and I'm Head of Education and Engagement at Timber Development UK. We'd like to welcome you to TD UK's new webinar series on engineering with timber. This series' aim is to add your engineering education, so as we transition to a bio-based economy, you have the tools and knowledge to include timber within the projects you work on, whether it's new build, retrofit, or extensions. So this is always IT problems. Here we go. Timber Development UK has formed from the merger of two of the largest and longest established organisations in the timber supply chain, the Timber Trade Federation and TRADA. Our aim is to connect the supply chain, lead best practice, and accelerate towards a low carbon future. And we know that timber has not been part of the engineering curriculum. So our aim is to, as it becomes accepted into the curriculum, to actually work around that and bring you this 7-part series. So our first webinar is an introduction to structural timber usage and properties. This talk will look at what we can achieve with timber design, and provide the basis for understanding the unique characteristics of timber as a structural material. We have two fantastic speakers with us today. David Trujillo, who's an assistant professor at Coventry University and head of biomaterials at Atelier 1, and Alan Dowdall, who's director and timber design lead at Ramboll. With that, I'm going to stop sharing and ask Alan to share his screen and take over the webinar. We will please post questions in the chat. We do ask you to keep muted, but you're quite happy to have your camera on. We want this to be very interactive, which is why we're doing it via webinar meetings. And yeah, let's head off. Alan, I'm going to stop sharing.
Okay, thanks, Tabitha. I'm going to attempt to share and get my presentation going. Can you guys see my screen?
We can.
You can, great.
Yeah.
Okay, so let's kick off with what we're going to go through today. So just a bit about content. I'm going to start off, do a little bit on timber examples, the things that we've done in the past, and show what sort of forms timber structures can take. And I'll do a little bit about, currently how the timber industry works a little bit. We'll then hand over to David, who's going to look at the science of the material and the material characteristics. And then I'll come and finish it off with a bit about some of the products, some typical framing, and then actually why do we want to be using timber? And there's lots of reasons why. So I'm going to narrow that down to focus on carbon, so the benefits that come with that. Okay, so timber design, what can be done? So I've littered this presentation with lots of visual images, so you can kind of see the things that are possible with timber and the spaces that we can create, and try to zone that into what are the typical framing arrangements that you tend to see within our buildings in general, actually. And I was going to talk about the benefits, but some of these images here, they do create really interesting environments as quite a calm feature to it. So this is the Centre for Cyber Security in Hertfordshire, where it's using a mixture of glulam and CLT. So framing methods, the common one is more of like a stick frame, so beams, columns, and then a panel then on top of that if you're doing all timber. And we tend to see a lot of them use it in resi, educational, or long span roofs. We have a deeper structure. and you can form your space with that, and that creates a sort of quite an open feel to the environment. Alternatively, go into a panelized timber structure, and there's lots of timber panel products available, and they're potentially more closed environments where you might have like a tighter space, like a residential or even a classroom. That you can form your timber from. This image is Dalston Works, which done quite a few years ago. I think it's probably still one of the largest timber buildings we have in the UK. And that was done pretty much all panels only from the first floor up. Moving on, you can mix everything, and there's no real answer to a form that your structure can take, and you can mix the framing and the panelizing. You can create some interesting environments, such as this space here, where and that actually uses a bit of steel as well. So we're using the material in the place where it works best. And also we've exposed the timber, and you get this sort of nice effect of expressing the structure and making the structure quite nice so everyone can see it. And moving forward with that, sort of hybrid approach, there's lots of examples of where it's have a steel frame and using the floor topping for the timber. This is 6 Osmond Road where we're involved now. What was quite interesting on this development, this image, is installing the stairs, which was a retrofit, and what was quite good in terms of using the timber here is almost the entire floor plate is what we call a soft spot. It has the flexibility to say create a hole, put some stairs in, and give the client what the space that they want. And then continue on a sort of hybrid theme. Some big open plan spaces like swimming pools and sports halls. It is quite good for a timber range. This is again a hybrid bit where we're using the timber and some tensioning elements, steel to create a sort of a lean structure to create the space within the pool environment. And then sort of finally thinking about volumetric, again using the panels. Volumetric has been quite popular in the past, where the panels just formed within a factory, lifted into place, and then connected together on site. And there's been various companies that have invested into creating these schemes. Okay, so quickly on a very short overview on how I've seen the certainly construction within the timber industry, how that has worked in the past. And you can probably break down a lot of the roles into 3 main categories for how the construction industry works. You have a client, and you can clearly see that this is a client. They're thinking about a building or a facility that they want to build, and then they're going to need a designer to realize that vision that they want to have. This is clearly a creative person as a designer, and when they have a design in place, they'll want a contractor to build that building. So there's many different roles throughout construction, but you could probably narrow them down into its basics form into these kind of 3 types of people. So how does it work? Well, we've got a client who wants to design a building, and this kind of works a lot with timber. We have a designer, and there might be even a PM who's sort of a bit in design role, coordinate everything, and they've got a contractor, and that's kind of a traditional view on how things have done. Certainly when it comes to timber, there's usually a subcontractor, and just not just timber, but lots of other things involved. And that subcontractor that person will become a client as well, and they may have a special designer, and sometimes that's a role we've filled in terms of doing some timber design, and that means that the subcontractor is, guess what, a client as well. So suddenly, if you haven't been in the industry for long, you can see that those roles can sort of start to merge, and bits of variations comes into it. And it may be that actually the designer that's been paid for the client will be novated to the contractor coming across, and that contractor then also is the client of the new client of the designer. Sometimes the contractor can get involved in the design. It can be a designer and they're employed by the client before they're novated across and novated into a different appointment in construction. That in terms of timber, sometimes you can get the subcontractor involved early in the design. They can advise the client in different ways of doing things and what's the most efficient way, for example. Or you can have the specialist designer who was under the subcontractor involved with the subcontractor and their client, and they're all clients. And you can just see that the point of this slide. The point of this slide is there are many different routes that you can go through to realize a building. There's no real right or wrong. It's complicated perhaps, but there's many different avenues. So there's no right or wrong way, but like a million different avenues to get from your client's vision in the early days to having something complete. And we try to focus that into a framework. There's usually the Ariba stage is quite good, and I also talk about when we want to involve some timber contractors, and that can vary throughout. So generally within our industry, they can be involved in different stages. It's always good to have advice from contractors, I think, earlier on, but it will also depend on the client's brief. So sometimes a client will want a timber building from the outset, in which case they may appoint a design team who have that experience, and so your appointment of a timber specialist may not need to be done until later on. But that's not always the case. Sometimes the preparation of the brief in the Ariba stage 1 means that you won't know what type of building that you want. If you want it to be timber until later on down the stages, and that could be in the concept design when you've sort of fine-tuned that brief aspect into a space and a frame that you want to have. And maybe that's when you have a specialist contractor, and it's all about when do you want to have the competency. So people who have the experience, competency to come into your team, when you either have them in the design team from the start, or you bring them in later on in the process when you feel like you need that experience to come in. And these kind of go all the way to the other end. I suppose one of the bits of if you have a design team who are involved earlier on and they have that level of experience in doing timber and maybe around the connections and things, and you can bring them all the way to stage 4. I think it becomes more of not necessarily design and build, but where the client has retained all of the responsibility. And these are the kind of things that you end up thinking about when it comes to the route you want to go to from certainly with timber. Sorry, somebody's interjected there. So that was very fast, and I realize I'm running short on time, so I'm going to hand over to David, and I'll come back later on to talk about other things about the science of the material from timber. David.
Hey. Thank you, Alan. I'm going to share my screen. Establish that probably the best way for me to go forward is this. Can you see my screens? My screen, everyone?
Not yet, David.
Okay, so I'll probably not click the. Yeah, here it is. Here it is. I'll share again. Can you see it now?
Perfect.
Yep.
Excellent. Okay, this is going to be a bit of a whistle-stop tour through timber as a material. So when we talk about timber, you're probably familiar with the terms hardwood and softwood. So what are softwoods? The technical term is angiosperms. They are primarily come from coniferous trees, which are mostly evergreen. So I have a photograph here of a coniferous tree, a larch, which is actually deciduous. It means it drops its leaves. The leaves of conifers are needle-like. The crowns are sort of conical. So you can think of a Christmas tree. And there are around 650 species, and they constitute the bulk of the forestry trade. So generally speaking, when we're talking about timber construction, particularly structures, we're talking about softwoods. And in the Eurocodes, we precede them by the letter C. And in this hardwoods, usually broadleaf, they're usually broad crown, and they tend to be deciduous, which means they drop the leaves in temperate and boreal climates. In the tropics, they'll be evergreens. There are a lot more variety of hardwoods. They're a lot more complex. And some of these species are very durable. So if you're going to be embarking on a project that requires very high level of durability, you might be using a hardwood in a structure, but that tends to be the only case you would really consider them, or for some aesthetic reason. And in the Eurocodes, they are preceded by the letter D. I'm quickly going to go through the structure of a tree trunk. So this is a sort of a segment of a tree trunk. We have two very notable areas. One is called sapwood, and this is the heartwood. Heartwood is a zone of the wood that has accumulated tannins and other substances over the years, and it's not active. This is, to a certain extent, the waste ground of the tree, so it accumulates a series of toxic substances here, which makes this wood very durable, a lot more than the sapwood. Then there is a very thin layer of cells here called the cambium, which are the only cells in the tree that have the ability to divide, and towards the inside they produce wood, and towards the outside they produce bark. And as they grow, you have two periods of growth in a climate like ours. We have early wood and late wood. I'll show you some photographs in a moment of what that looks like. So here you would see like a ring, and you see that some pores are a lot smaller and some are a lot bigger. So this is what we would call late wood, which grows in the summer, and early wood, which grows in the spring. You also have an image here of something called array, which are cellular structures that radiate outwards from the tree. Here we have a vision of the radial section. So you see some cells are running upwards and some are radial. And the most important cells are the ones that are running upwards. And here you have another view. Here you have the ones that are going inwards, and here you have the others. So what are going upwards? Generally, the ones that provide the mechanical strength. They're transferring also fluids up and down, up the tree, and they're storing nutrients in the parenchyma. But the key thing that we're interested here to note is that the majority of the cells run along the tree, and those are the ones that are most fibrous. And that affects the mechanical properties of timber, because here I have a photograph of two pieces of wood that are being tested in different ways. This one was compressed parallel to the fibers, to the grain, and this is the result you get. So you get a lot stiffer, a lot stronger behavior than when you do it perpendicular. Here you see how it sort of gets crushed like a sponge. And fundamentally, when you're testing it perpendicular to the grain, you're sort of collapsing those cells, where here you have to push against them. So you have a material that's a lot stronger and stiffer in this direction, and less so in perpendicular. And that's a really important characteristic of timber, because it means that its properties depend on the direction of the forces. When we design with timber, in the UK, we tend to use either C16 or C24, the most common timbers that we're using in construction. You have to look up the properties depending on the stresses you're applying onto the timber. So if you're bending it, this is the characteristic strength, which is not the same as mean strength. It's roughly the 5th percentile. And take here an interesting case of tension. Parallel is about 20 times larger than perpendicular. And when you have compression, parallel and perpendicular, there's a sort of about 7 to 8 times difference between one and the other, the one I'm showing you. And the same goes for the modulus of elasticity, the stiffness, which is substantially larger in one direction than the other. Another important characteristic of wood is how it interacts with water. So when a tree is alive, it has water inside its cavities of the cells, but it also has water in the cell walls. As a tree is cut and it starts drying out, the first water that is released is within the cells. And then when you reach at a very important value of around somewhere between 25 and 30% moisture content, what's known as the fiber saturation point, the water from the cell walls starts being released. And then the cell walls water in the cell walls starts getting released, then we have changes to the properties of the timber. It shrinks, it becomes stronger, stiffer, and more brittle. And so moisture has effects, as I said, on strength and stiffness. Here we have two pieces of wood that were same size. They're both clear wood, so they have no knots or anything. And they were tested in bending. Here you have one that was saturated, so it's less stiff and very ductile, so you have a lot of plasticity and you have less strength. When you dry it, you have greater stiffness, greater strength, but more brittleness. Another characteristic of timber is that it behaves in a sort of a viscoelastic manner. And I think the only other construction material that I can think that has sort of viscoelastic properties that you can relate to is soil, really. You have creep behavior, and you have also some behavior in terms of how strength behaves over time, which is a peculiar characteristic. So the first thing to bear in mind is that what this graph represents. Here we have on this axis time, and here we have a deflection. So imagine, in your mind's eye, imagine a beam that you've applied a load onto it. So what would happen is that you would instantly observe a deflection. However, over time, that deflection would increase. You can sometimes see that with shelves, that over time, with a lot of heavy books, you might have an increase in the deflection. Now, if you remove that load, maybe some years later, you would have an immediate recovery, but you wouldn't get to the original position. Over time, you might recover back a percentage of the original deflection, but you might have a permanent deformation. So these are some of the characteristics of timbers, but we have a phenomenon called creep, and that is that deflections increase over time. There is another characteristic that's quite hard to picture, and the only way I can sort of explain it to people is that just timber seems to get tired. It's a material that's evolved to resist short-term loads, namely wind loads, and so when you apply a long-term load, it behaves in a different manner. So our benchmark is a standard test, and when you test timber, you have to be very strict about the duration of a test. So let's say 5 minutes. And so if we had, again, a piece of timber in bending, and we got a certain amount of resistance, you would consider that to be the 100% of its strength in the standard test. If you applied a load much faster, say something like a gust of wind or an earthquake, actually, you would see that timber exhibits higher strength than what you observed in the test. And the same is the opposite. Here, this is a logarithmic scale. When you're looking at something like design life, for something that's going to last like 50 years, you'd only be considering something like 60% of the strength you observed in a test. So time is a very important consideration, as well as moisture content, to understand how strong, or to predict how strong a piece of timber is going to be. So that is to introduce two concepts that will come up during these sessions that are from Eurocode 5, that once I've sort of set the context, you'll sort of, hopefully you'll now say, I see where they're coming from. One of them is K-mod, a very important factor in Eurocode 5, because the majority of the numbers of K-mod are less than 1, smaller than 1, and it's a factor. So fundamentally, it's a number that reduces the strength of the timber most of the time. So if we have a timber in what we call service class 1 or 2, and these are the situations where the moisture content of timber is going to be around 12 to 20%, then we would pick a K-mod value. And so this value goes from, in some instances, greater than 1, so somewhere around here, for drier timber, and sometimes less than 1 for design life of a building. If it's in service class 3, which means it's outdoors, then this can be actually something like 55% of the strength that you would have used normally. So this is a concept that's important. We need to remember that we might have to reduce strength on the basis of the moisture content and the low duration. There is another concept called KDEF, which is a factor, a number that we use to account for the amount of creep when we're doing serviceability limit state calculations for deflection, for example. So depending on how dry the timber is or how wet, so drier service class 1, wet service class 3, the amount of creep to expect. One of the things that's important to bear in mind with timber, these are some tests we undertook in our lab of some identical or seemingly identical piece of timber that were clear wood. That means they had no knots or anything. And yet they gave us very different resistances to when loaded and different behavior. And that is that one of the things with working with natural materials is that they're variable. And what we want to do through a series of tricks is go from a material that has a lot of variability to one that has less variability. This green sort of normal distribution represents that. And that is because when we are designing, we pick something called the 5th percentile, the characteristic value, which is roughly the 5th percentile, which means of all this population of results, we design with sort of this strength. So if we can reduce the variability, that means we can assume a much higher strength in the material. How do we reduce that variability? One of the ways to do that is through grading. So we pass timber through a machine and we try to infer the strength of the material. It's only a statistically valid inference. It doesn't tell you exactly how strong the material is because there's only one way to know how strong it is, and it's to break it, which of course wouldn't be any use. But it helps to reduce the variability and helps to control for known defects. The other way we can control and reduce variability is by making engineered timber products, which Alan's going to talk about a bit more. So we can make products like LVL, which stands for laminated veneer lumber. We can make CLT, which is cross-laminated timber, Paralam or glulam. Engineered timber is really, really exciting field. There are many advantages. So we reduce variability, we remove defects, we can create very large elements, we can adopt novel shapes, we can reduce anisotropy, we can limit dimensional changes, we can avoid distortions. And so it is a field that revolutionizes what we can do with timber compared just to using sawn timber. One of the things to bear in mind with timber is that it is a biogenic material. It is destined to biodegrade, which actually is a good thing. Nature's got a way to get rid of a material for us. You know, we've got all these problems with plastics now because we don't have a way to get rid of them naturally. However, the role of the designer is to slow or stop this process. So here I have a photograph of a temple in Kyoto. And I love this photograph because this is a temple from the 13th century. So it's been around for a while. And it's been around because the designers were wise in its use. So one of the tricks is that it's lifted from the ground, so it's not in contact with the ground. So that's one of the sources of wetting that reduces the durability of timber. got large overhangs, which again protects timber from wetting. And the third thing is that air can circulate through the structure. So the fundamental principles to making a structure durable is to adopt a concept known as durability by design, which is to keep timber dry, drained, and well ventilated. Other means to increase durability are chemical preservation or choosing, as I mentioned earlier, durable species. However, really important to note this, you cannot make good a bad design by choosing a durable species or chemical preservation. It's really hard to undo a mistake in design by these methods. As we all know, timber is a combustible material, but there are things to bear in mind about timber when it is not readily ignited. You need really high surface temperatures in the absence of a flame, in excess of 400 degrees centigrade. And in the presence of a flame, still in excess of 300 degrees centigrade. So fire in any building tends to start not in the building fabric, but somewhere else. And it has several advantageous properties. Timber burns at a slow, predictable rate. Timber is a poor conductor of heat, so you won't have damage by thermal expansion. And you only lose strength in a timber element as a loss of the cross section. And because it burns at a slow, predictable rate, we can predict how long we are going to have a section being able to carry load during a fire without any sort of unpleasant surprises. And the thing to bear in mind is that combustibility depends on surface volume ratio. So if you want more fire resistance, you might go for something large with a small surface area like a glulam beam, even though maybe a truss would have been a better use of material because a truss would have a very high surface area. It's important to note that fire resistance is the ability of a building item or element to fulfill a specific requirement during a fire test for a given amount of time. Now, one of the things to understand about fire resistance is it's not a material characteristic. It is a system characteristic. So you can make a fire-resistant structure out of timber, provided you consider things. What is fire resistance? Fundamentally is that a structure remains stable. It must not collapse. You retain integrity, so fire must not penetrate. And insulation is that heat must not transfer from one space to another. So it's all about how the system comes together. It's not to do with materials per se. How can we improve timber's fire performance? One, you can probably infer from what we discussed, is you can oversize members because of this characteristic of the charring rate. So you have members which are larger than needs to be, so that you have some sacrificial material. You can encapsulate the timber, which is like putting it in plasterboard, or you can apply fire retardants, which may slow down the process of ignition and spread of flame. Okay, that's the end of my part. Let's go back to Alan.
Okay, thank you, David. I'll share my screen again. Let me know when.
It's perfect. Yep, it's all up.
Okay. So I've got 30 slides and 5 minutes. Let's see how we crack on with this. Timber engineering products. We've been through sort of some examples, procurement, a bit on the science, and I just think about what is available out there in terms of products. Just quick one about this image. This is Alan Dowdall Sports School. It's mostly all timber from the superstructure up, and this is made from cassettes, which I'll talk about in a minute. It's a CLT and glulam cassette. Okay, there are a whole range of different timber products that you can use that are available in the market, from very simple sawn timber all the way up to highly engineered cassettes and combined types of mass timber products. So that in this image, the range of how engineered the product is sort of starts off low on the left-hand side and gets, I suppose, much higher engineered as you move across, and consequently, the cost tends to get more expensive as you move from left to right, but also the ability to do things with different types of buildings. The scale of the building can also get bigger as you move from left to right. Quite a lot of the modern buildings, larger scale buildings, are going to be using these type of products, so the glulam, CLTs, and onwards, and LVL, laminated veneer lumber, as David mentioned. They are quite popular. On the other scale, sawn timber joists, OSB, and those kind of things, they tend to sit within domestic. Of course, there is crossover in some of those, but that's a generalization I would put on top of these types of products. Okay, so moving into an example of, say, grids and arrangements. I'm just going to take a live project that we've got in terms of what we're looking at, and in this case, it's a scheme in London. We've got this retained facade, but I'm not going to do that today. And typically, for a lot of our commercial, certainly sector timber buildings, we have a concrete core, which is great for stability, and the floor plate then is can be constructed from a timber of some sort, and that's generally open plan, so it'd be a frame of some sort, which is following sort of the first framing arrangement I showed you guys at the start of the presentation. So if we think then about our available products, and this is quite a tall building, so we are certainly within the mass timber elements of it, and maybe even the combined mass timber. But for this example today, I'm just going to focus on probably the most popular, which is glulam and cross-laminated timber. So types of grids, how can you play around with that arrangement? This is the first one, what I call the most efficient, and that's because your panel, in this case the CLT, was oversailing the top, and you can get continuity with that, and it's also quicker to build, and there's less cutting, and efficient in terms of transporting material. Depending on the size of the grid, that could be potentially quite deep. So an alternative way of doing the grid is to chop things up a little bit and move beams into the height of the floor panels. So you get a shallower construction depth, and that can help with building height, or overall floor to floor heights, things that play a factor in design as well. I've shown on this image that typically there might be a tie beam going across, or you can use the CLT to tie things together. That will be limited on how many stories you can get before that becomes unviable. So we're not dealing with many stories in this particular example. Then going a bit more extreme, sort of if you're almost replicating what a steel frame could look like. You can start to have primary and secondary glulam beams. I think this is probably less popular because it's quite dense and heavy, but we have done it in the past. And they're just some examples of grids. But what I would say, sometimes just forget about a grid and go for what's right for the space that is you're designing in front of you. And this is I think a sketch from a couple of years ago, which is now on site, where we're looking at creating the most efficient use timber wise, and also the most adaptable in terms of using the CLT in its a little bit of a secondary span that can allow for service distribution with a flat soffit and the like, and that's worked out quite well. Coming back to original example, where does efficiency lie in grids? So if we have the first two, what we find generally is all timber, forget about steel for a second, in that our efficiency tends to be on for CLT spanning itself around about the 6 meter mark. You can go further, you can, 7.5 perhaps, but it gets quite deep, and that just sort of adds to cost and various other factors as well. So a typical grid with this kind of arrangement can be 6 meters, say by 7.5 on the glulam, or you can push it out to 6 by 9. You can go further, but really there are probably other constraints that will make that either unfeasible, or if you go really far, I mean, you're not going to get a 15-meter floor on a typical office space in the UK. You're going to have some deep structure if it's all timber. I mean, steel grids could go 13.5 or more. So with composite action and concrete, timber, you have to work with the material. It does have different characteristics for other material, and you need to account for that in your design and the space in the grids. And just finalizing this with the layout we showed earlier, maybe if there is a primary and secondary beam, and we can perhaps push that out, maybe keep the same spacing in one arrangement, but push it out further into, say, instead of 6, more like 7.5, and reduce the number of columns within your frame. So that's a quick overview of perhaps where you can go with in terms of a layout, and these are all early stage sketches that can help along to if your designers influence the design in ways that work out best for the client. We talked earlier, and the vision that they have for the scheme. But why use timber in the first place? What's the benefits? And I am going to be slightly biased. I think timber is a wonderful material. It has a lot of benefits that can work out in its favor. It's a very low carbon material, so the embodied carbon within the structure is really low. It is a renewable material, so it grows. We'll cover that in a bit. And there's various other bits. It's quite fast to build. It's very lightweight, and the spaces that it creates generally have a high health and well-being credentials to it. So, and those images from before where you see that it's exposed, there is a warmth that comes with it that creates a quite a serene environment. So I'm not going to touch on all of them, but I'm very briefly going to go through, say, a bit about low carbon. So this is what you're looking at here is a graphic on getting timber from its source to site, and the amount of embodied carbon used to create CLT panels. So there is an element of sequestration that happens within timber. So as timber grows, it's sucking in carbon from the atmosphere and capturing that in the fabric of the timber. So that's what the negative bit is, and then the plus bits down here is the number that comes with just harvesting that and producing the panels and so forth. So if we compare that, say, to concrete, and I'm using a typical grade concrete with I suppose an average, a typical amount of cement replacements on it. So you can see that there's quite a difference in the material. These are meter cube rates, but the changes in when you look at on a floor plan between the concrete and timber, they're not too dissimilar to what you see here. If I compare that to, say, British steel, open sections, it's quite a jump. And if I'm honest, I'm being a little bit disingenuous to steel here, because you don't really use meter cubes of steel, billets of steel, when you're building their fine-tuned products to work as efficiently as possible. So if I compare a typical beam, these are two beams. One's a steel beam, timber beam. They have equal stiffness. You can see that just from the characteristic properties, the timber is deeper and wider and has more material in it compared to the steel beam. If we look at then how that compares with, as opposed to just a cubic rate for the embodied carbon, there's still quite an order of magnitude difference within the material. As a designer, I focus on the embodied carbon number as for the early stages, certainly. I'll talk a bit about sequestration in a minute. But that's about low carbon, some broad numbers. Just thinking about that renewable bit, this is a sort of interesting statement where I don't think we've fully understood the vastness of some of our forestries around Europe and in Austria. You know, if you can, on a good day, if you get a meters cube of growth in timber and all that carbon that's captured, it's quite significant. I mean, so it just shows that there is a lot of resource out there. Now, obviously, that's even if it's not quite exactly a meter cube, it's half a meter cube. I think it's still quite an interesting number. I'm just looking at sort of how the processes work and when you're looking at carbon and taking account of that renewability aspect. You know, when you build a building, that's the A1 to A5 bit here. You know, there is amount of carbon that's thrown out into the atmosphere. In usage, it'll be embodied carbon the same, there'll be operation carbon, and then when you demolish the building, there's amount that is then also put into the atmosphere in terms of the energy used to demolish that building. From a timber point of view, you can see that there's some biogenic, and that's the sequestered carbon that's stored within the building, and at the end of life, then something will happen to that, and that will get released again. I think that what we really want to be doing, and there's lots of thought leadership on what do we do with our urban forests, as we guys call them. If we have use for that, once we've harvested that timber, we want to be capturing that carbon and keeping it within several building life cycles, or even extend the building of a life cycle, the length of the life cycle. Sorry. So what David was saying about that durability is really important. You know, making sure that the timber is in the right place and that any sort of water drains away from it to extend that life. But sometimes it will just naturally fall out of its building life and something will happen. We want to be finding ways to actually reuse that timber where it's good. And I think that's where you know, the urban forests are going to be. And we've got a lot of timber within our cities that once it's finished its life cycle, it either gets burnt or mostly burned, to be fair, or regurgitated into panels, but most of it is burned. So I think there'll be a going forward in our industry, a lot of research into the use of sort of secondary timber, and that's where there's a bit of as Colin Rose is looking at secondary cross-laminated timber, secondary timber, and trying to find a way of having that timber as a resource and then putting it into upscaling it almost into a product that's quite usable, and we've helped him with some funding on his research. Okay, I have rattled through them pretty quickly, so there is a little bit of time left for some Q&A if anyone wanted to ask any questions. So I'm going to stop sharing. I think there's some things in the chat.
Thank you, Alan and David. That was absolutely fantastic. There are some questions in the chat, and there have you've both been very busy multitasking, answering them. I'll just ask one that's coming from Luca, which I think it's not actually in the you know, just put in the chat to everyone so we can all see. From Luca, Alan, can you touch on what to expect from the Building Safety Act coming into force next month in terms of roles and possible encroaching with CDM and or building regulations? Is that?
I'm not sure that's solely related to timber. I think that's an industry-wide thing where there's a whole fundamental change that will come through. So I don't think timber has got a standout difference within that.
Understandable. David, this is for you. What could the UK do to stop being one of the largest importers of timber?
That's a very interesting philosophical one. I think that I bounce that one back to you, Tabitha. I think I'm going to be. I think we could grow more timber in the UK, no doubt. I think there have to be incentives for farmers to pass their land from whatever current use they've got their land to become forestry. We have some land that, in my opinion, is poorly used because the incentives are for it to be used for certain purposes, like sheep farming, dare I say it. But it's, in my opinion, I'm not a farmer, so I might be very wrong here. It seems to be quite an inefficient use of land, so maybe we could have more of that. But I don't think necessarily importing timber from our close neighbors is necessarily a bad thing either. We have the forests of Scandinavia at our doorstep and others, and shipping is, if this timber comes on boats, it doesn't have a particularly high carbon footprint because it's not coming from far and it's being transported on boats. So I don't think we have to get too hung up about the fact that we don't have our many UK forests.
No, thanks, thanks, David. Right, we'll do time for 2 more questions. There's 2 in the chat, so I'll just ask them. Thank you, Raffaele. How do timber costs compared to concrete and steel? You know, on a typical building, are either of you able to?
It's a changing dynamic, that one. What I would say is it's not it has to be a holistic cost comparison, and those costs, you know, over time they change depending on the economic, social and political landscapes, and the only thing you can do is compare it at the time, but you have to take, you know, the benefits and the pluses and minuses of each option. So if you have a concrete frame, if you take out the concrete and replace it with timber, it's going to and use that as your cost plan, that will be more expensive generally, but there are other benefits: the speed of construction, the lightweight nature of it. Can you save on the foundations? Can you save on the fixings of your services? Pre-install windows, all those kind of things, that pre-order windows. So the whole program can change, and that can have a massive implication on your costs as well. But also, you know, I've done many schemes where I've just taken out deep foundations, and that's saved on time and cost and carbon, massive amount of carbon in deep foundations. So that I think if you go into it with your eyes open on those kind of things, you will come to the right answer. It's the raw material costs that vary. So you just, as long as you have your finger on the pulse on that, then you know where the cost effectiveness lies.
Thanks for that, Alan. And the final question from Joshua: what are the main roadblocks in replacing concrete slabs with CLT, for example?
Who are you going to give that to? Do you want me to do that?
I'll let you do that one, Alan.
Right, okay, yeah. So just repeat the question.
Sorry, everything just keeps moving in the thing. What are the main roadblocks if you're looking to replace concrete slabs with CLT slabs? Are there any?
I mean, the roadblocks are who's your stakeholders. They're the ones you need to engage with. I think the technical bits can be solved. You know, the from a structural point of view, you can make most things work, and if you're able to you know, say a few compromises. I think the blockers tend to be, you know, have you got, you know, your fire engineer and the fire aspects sorted? Have you got your insurance people on board from an early point of view? They're the main stakeholders that probably need more engagement with than perhaps if you're doing out of concrete, because it's so much more. It has or it's felt like there's more. Certainly those stakeholders have more experience with that material than they would have with timber. So you need to understand who they are at a certain stage, have a chat with them and say, this is what we plan to do. So
knowledgeable work to increase your clients' knowledge, and then work with a team of professionals who definitely understand timber.
Yeah, I mean, it's just knowledge sharing at the end of the day, and communication. Which
is what this whole webinar series is about. So that was perfectly winding up. Alan, David, huge thank you for coming and sharing your knowledge, so that, you know, our current and future engineers know how to use timber better. We do have some resources on the website. So if you head to Timber Development UK and audiences, or just go to engineers, you will find 3 engineering books we have available free to download. We're also running a student challenge next year all about timber and housing. So again, if you would like to come and join us in that, it is for students. And we carry on with our series of 7 webinars. So if you're not busy next Tuesday, which I'm sure you won't be, come and join Alan Davis from Cardiff University and Gavin Knowles from the University of Bath, as they're going to talk about timber beams and joists. Thank you so much all.
Thank you very much, Tabitha, and everyone who's joined in
Thank
to
you.
listen.
All right, thank you.
Thank you.